Good afternoon, Rich Nass, Executive Vice President with Open Systems Media, leader of the Embedded Computing Design franchise. I am here for a video that's sponsored by PICMG, where we're talking about COM-HPC. This is a very new specification, actually hasn't even officially launched yet. That'll happen sometime in January, I believe. So this is one of 8 videos, and in each of the 8 videos, we're talking about a different segment of the specification. Here in this video, I'm with Henk van Bremer. He's a Senior Product Director of Modular Computing for ADLINK, and we're going to be talking about the server part of the specification. In one of the other videos, we talked about the client aspect. Now we're talking about the server aspect. Henk, did I get that right?
Yeah, you got that right. I'm going to do that today, and excited to be here.
Perfect. So before we start, just very quickly, what is the difference between the server spec and the client spec?
The client spec is basically graphic oriented, while the server spec is headless. There are no graphics, and these signals are substituted for more PCI Express, more Ethernet, higher speeds on the Ethernet side.
Perfect. Okay, let's hop into the presentation.
Okay, so welcome to this presentation for the server part of COM-HPC. I will keep it light because others will dive into greater detail of COM-HPC specification, things like IPMI, which is a science in itself. The name COM-HPC already clearly sets the computer module apart from other computer module form factors because the name stands for high performance. I first want to go back a little bit to COM-Express that actually tried to target the same high-end market. Over the last 4 years, COM-Express saw the addition of the so-called headless Type 7 server variant. Pinout for graphics was substituted for more PCI Express, and high-speed networking was added in the form of something like 4 10 gigabit Ethernets. With that addition, for the first time, fiber optics were usable on the carrier boards. From our experience working and designing on this Type 7, some shortcomings came to light when the more high-end silicon entered the market something like 2 or 3 years ago. One of the things was power consumption. It was driven up to something like 80 or 90 watts. That's technically not an issue for COM-Express, but on a small form factor, 125, 95 millimeter in size, it became a challenge to make efficient thermal designs. What was actually the biggest drawback is the need for higher memory capacities. With SoCs supporting something like 20 cores and virtualization being used more often, we saw an increased need for larger memory capacities, sometimes up to 128 gigabytes. So to populate 128 gigabytes with 3 or 4 SODIMMs, it's a really very expensive exercise because you go to 32 gigabit SODIMMs, and these things are not mainstream in the market. So there you're going to a very expensive area. Lastly, 10 gigabit Ethernet supported on Type 7 is quickly being overtaken by higher speeds in the market. We're seeing 25, 40, and 100 gigabytes now becoming mainstream. So this is explaining the need for a new COM-HPC specification. So let's step a little bit further back and look at some of the reasons that actually caused the COM-Express Type 7 and our COM-HPC to emerge in the first place. Actually, the reason for that is very, very simple. It's the exponential growth of data and to need to process that in the embedded process. We already saw in Industry 4.0 that is actually already coming online, and IIoT that we saw an exponential growth of data from sensors, actuators on the work floor. In the coming years, we also see AI being added to these processes and 5G. So I think all the verticals are going to be, touched by this new kind of technology, and this is going to generate an even more massive amount of data in the industrial processes. Because of latency considerations and tremendous communication cost, data will have to be processed at the source and acted on in real time. So this is typically edge computing, and that's the major growth driver for the embedded market in COM-HPC. So On the right side, you can see what an actually COM-HPC server module will look like, or looks like already. This is a design study that we did. So let's again summarize the reasons for COM-HPC. Simply, edge computing is the fastest growing segment. High-end embedded multi-core processors are finding their way into the embedded market, and memory per processor is increasing to 256 gigabytes or even more. Existing popular form factors such as COM-Express technically cannot address this kind of market. So this is where COM-HPC server type comes into play. Applications for COM-HPC as we see them. I think we separate three groups of applications. AI, obviously, what I already said, this is going to be one of the main drivers, and this is where we will see PCIe by 16 GPU FPGA connections for parallel processing. Since most of these designs will be multi-vendor, I mean, graphics and CPUs not always come from the same vendors, we're basically talking about heterogeneous arrangements. And this is where the PCI Express bus speeds are very, very important. We see that basically everything that will be able to drive, fly, or float is going to be affected by AI and will have a co-pilot or will be fully unmanned or fully automated. Things like hard to come by skills, surgery, for example, will be AI'd, whereby the current expert becomes a consultant for AI implementations. The second part is the task consolidation. I already said we see virtualization entering the embedded market. An example is trains, where nowadays we have something like 5 or different kind of services like a reservation, Wi-Fi on board, video surveillance, that is being delivered by different vendors in different boxes. And we see that these kind of processes are being consolidated in single machines. And that's where you see the need for virtualization and then the higher memory requirements. And then the last part is rugged, of course, typically also for COM-Express, and a special purpose where the things have to be designed based on the environment, and the board sizes are being dictated by the enclosures instead of the other way around. So this chart, we see the position that COM-HPC takes when we compare it to COM-Express. Again, COM-HPC is not defined to replace COM-Express, but it's merely to extend on it, moving into higher power and higher memory capacities. So we see on the left side COM-Express, everybody knows this, something like 12 watts for the mini size, 15 to 25 watts for the compact size, and around 60 watt nowadays for the COM-Express Type 6 and Type 7 basic size. COM-HPC client, which I will not talk about a lot today, extends into 80 to 90 watts. And then if we go to COM-HPC server, we will see 150 watt CPUs. And I think there's even a stretch to go to almost up to 200 watts. The form factors, again, left side is the server. On the right side, you see the client, and we put in a picture of a COM-Express to see how these sizes compare. You see that the A size looks a little bit like the COM-Express size. And then we get the B and C size, that the C size is actually expanding the amount of memory you can put. You can put 4 SODIMMs, 2 on the rear and 2 at the top. On the left side, the server side, 8 memory sticks, 8 memory DIMMs, and on the right one, we do 16 memory, 8 memory DIMMs. A new high-speed connector. This is a picture of a Semtech connector. High density, we get 2 times 400 pins on the boards. Both the client and the server will use the same arrangement, mechanically the same arrangement. On the left bottom side, you see what actually goes on the module, and the middle and the right is what goes on the carrier. For the carrier, you can choose between 2 heights. One is 5 millimeter, the other one is 10, and the 10 millimeter gives you a lot of space underneath the module where you can put almost any component available in the market. There's, you will not get into problems there. Fast speed, we're going to go up to PCIe Gen 5. Okay. Then the server pinout. I'm not going to go in great detail. I will pick 4 subjects: power, PCIe, IPMIB, and USB and Ethernet. We will look at it in some next slides. The power input, what I already said, it's a single 12-volt input. D-rated, we can input something like 350 watts. And then if you compare it to the 150 watt CPU, there is actually still a stretch to go a little bit higher on the CPU side. Then there is a strange addition, a little bit strange because it's the first time actually that has been done. It's called PCIe target. These are control signals that will allow you to make the COM-HPC into a kind of device. So I would be able to put a GPU on it and pair that COM-HPC with a server, typically host the COM-HPC with a SoC or a CPU on it. Then USB 4.0, we don't really expect for the silicon in the market. It's targeting that's headless that they will go into 4.0 anytime soon, but it's there for the future. So IPMIB, I will extend on that also in a slide later on, and Ethernet, that's what we're going to look on in the next slide. So we're looking at the Ethernet signals. There are actually 2 groups of signals, both that have their own sideband signals. Every KR can either support 10 gigabits or 25 gigabits. And if you group these things, you can go up to 40 or you can go up to 100. In the next slide, we will see that for cabling, which is actually the PHY is being chosen on the carrier. Cabling, we got a lot of new options for cabling. We can go up to something like 10 to 40 kilometers on fiber, and we have short haul copper cabling. Then looking at memory, I already said COM-Express used to be a problem there because for high memory capacities, we get into very expensive areas. The slide shows that even if we would approach the need for something like 512 gigabyte per module, pricing per gigabyte will not be very excessive, as we saw what I said on COM-Express. Normally, every memory controller would be equipped with 1 memory stick to achieve the highest bandwidth, of course. To not get into US dollars, I merely indicated in this slide the percentage of price difference between compatible solutions, just looking at the capacities. So what we can see in this slide is actually that the sweet spot for memory already moved to 32 gigabytes per stick. And even if you would go to something like 64 gigabyte per stick, you would only get a 5% price disadvantage. So that means from 128, 256, or 512, we will get a good price performance on capacity. One of the last slides, out of band management control. This is typically called IPMI. Many COM-Express form factors have over the years supported something called API, eAPI, that was specified during the initial COM-Express specification round. eAPI typically focuses on lower level embedded functions that are not abstracted through drivers, such as watchdog display brightness, backlight control, logistics, and EEPROM storage. While COM-Express will still support eAPI, on both client and server, the COM-HPC server type will step up and support full IPMI because it's kind of a requirement in the server market. So possibly we will support an OpenBMC variant and the more costly, how to say, just licensed variant as they are being sold through several bias vendors. So this diagram shows a typical implementation of IPMI in combination with a modular form factor. You can compare this 1-to-1 on what has been done for ATCA with AMC modules. AMC modules are actually also kind of computer modules. Thereby, you get an MMC on the computer or module, and you get a BMC on the carrier. And the BMC can then further, how to say, just communicate with the shelf manager. So in a picture like this, you could actually populate 2 or 3 modules and still have a KVM access to all of these 3 modules. So that's about it. This concludes a brief overview of the main points that we set that sets the COM-HPC server apart from the client part and from other existing computer module frame factors. The PICMG COM-HPC module specification is ready around January, and there is also going to be a carrier board design guide that will be released a couple of months later, I think. The COM-HPC form factor definition that was initiated by Congregate Control and ADLINK in February 2018 has been a very, very long trip. It lasted almost for 2 years. As usual, it has been a very close cooperation between competitors in the embedded field to come out with the best possible result for all, both for our module manufacturers and also for our customers. Thank you for your attention.
Thank you, Henk. That was really informative. One thing that I did want to ask you, though, I haven't really heard it come up. Do you expect COM-HPC to be used in any harsh environments?
Yes, we do. Of course, it will go. Of course, if you go to server level, it will be around -20 to 70. But definitely on the client side and the server side, if we use low power silicon, it will definitely go also into the -40, 85 rugged designs. But with high power, we will have to step up on enclosures. I do see water-cooled enclosures coming up in this area.
And it has the ability to deal with shock and vibration as well?
Yes, absolutely. Yes.
Perfect. Okay. Well, thank you very much. That was Henk van Bremer. He is a Senior Product Director of Modular Computing for ADLINK. And as I said earlier, this is one of 8 videos. I encourage you to look at all 8 of them. You'll really learn something, a different aspect of the new COM-HPC spec in each one.